So now to do the actual proof, I want to assume that some two lines do not intersect. And I want to state that in a mathematically rigorous formal way so that I can use it. And the way that I state that is, suppose that L is not equal to M and that they are both lines, right? That's saying I have two distinct lines. From this, I would like to prove that their intersection has at most one point, and I want to state that mathematically rigorously as well. And that's down here at the end of the proof. And the way that I state that is you cannot have some 2 points in the intersection that are distinct, right? I mean, if they were equal, then you'd really just have 1 point. So I want to talk about 2 distinct points, and this is how I write it. And so I want to get from line 1 to line 6, how do I do it? Well, by the way, notice that this is justified by just being given. It's an assumption of the problem. Okay, I use a technique of proof called proof by contradiction. And in fact, it is a somewhat common sense kind of argument style, one that I think we use somewhat frequently, even if we don't really know that we're using it. So an example would be, suppose a lawyer is trying to defend Mary, and Mary is accused of murder. And the defense attorney says, well, assume that she committed the murder. And then says, well, she was 10 miles away, 10 minutes before the crime. You know, if she were the murderer, she would have to travel an unreasonably fast speed and clean up after her, tracks and so on. And therefore, we've reached something unreasonable. And if we have come to an unreasonable conclusion, it must have been that the assumption was also unreasonable and must be false. So in math, we will often reason in a similar way. We will assume something for the purpose of reaching a contradiction. Once we reach a contradiction, we will know that the assumption was wrong. So that's a proof by contradiction. I signal that I am starting off a proof by contradiction by writing a bar next to my lines indicating the start of the proof by contradiction, and then also ending once I have my contradiction. So I assume that I have 2 distinct points in the intersection LM, right? I call these 2 points EF. If I reach a contradiction, I know that that can never exist. Okay, how do I go from here? Well, if EF are in the intersection, then EF must be in L, because after all, the intersection is the set of points in both of them. So if it's in both, it must be in L, and it must be in M, right? E and F must be in M as well. Well, by axiom 1, 2 points on a line mean that the line determined by E and F is exactly equal to L, right? The 2 points determine that line. They also determine line M. So the line EF is equal to both of these. Now I'm going to use something frequently used in mathematics. It's called the transitivity of equality. Now, it's, again, a common sense thing stated rigorously, which is if you take any 2 things, whatever they are, A and B, lines, points, whatever they are, if they are equal, and then B is also equal to C, then A is equal to C, right? If this is the same as that is the same as that, then the first thing is the same as the last thing. It is common sense, but we call it the transitivity of equality. And that's what we have in line 4. L is equal to line EF is equal to M. So L is equal to M. Okay, L not equal to M contradicts L equal to M. And then we get to say that line 2 must have been false, which is the same as saying line 6 is true, right? Line 6 is the contradiction of line 2. And that's the end of the proof.